Yeah, we have already had the different points of view on proteins in the morning, and I'll add a completely different view again. So typically, the most frequent approach to proteins, I would say, is to see proteins as molecules. Well, they are molecules, of course. Well, So you have small molecules like water, and then you just do the same things but on a bigger scale. You have more atoms, more bonds, and so on, and you have a big molecule, and this is lysozyme. Cheating a little bit because there's no hydrogens on there, so it's only half the atoms. But so this, I think, most of the theory of proteins is built on this idea that it's you see that in the choice of coordinates and the choice of approximation. So, and I would like to propose a different point of view, complementary point of view, which is proteins as things. There are big things like this one, and there are small things like this one. But you could, in each case, say, well, these are things which are described by having some shape and being made of some material. So for the shape, I mean, this is pretty evident. So, well, you can define lots of molecular surfaces. The details don't really matter. So what I want to discuss is the other part. So if proteins are things made of a shape, defined by a shape and a material, what is the material? So the material is, well, the folded peptide chain. And just to say that material doesn't mean it has to be homogeneous. So the potato is more or less homogeneous at the length scale we look at it. But you can have things like reinforced armed concrete here, for example. You have two different materials, composite materials. So if one is the bulk and the other one is reinforcement, you will see that I will do something similar for proteins, propose something similar for proteins. So don't let the word material let you think that this is just overly simplistic. Although I should also add that I'm actually not really there. This is a goal for the future. Where's the red dot? No, okay. Okay. So the idea is that to look at a construction material for proteins, which is, of course, made of peptide chains, folded peptide chains. So for me, they are folded. I'm not interested in how they fold and why they fold and all that. So it's there. I'm interested in describing the behavior of folded proteins. And then the idea is I would start from looking at macroscopic properties, as one would do in material science, and then go to smaller length scales and see what you can add to get something more of the molecular character back without going to really description at the atomic level. Things like heterogeneity, you can have water pockets or ligand pockets, this kind of stuff. You have local anisotropy necessarily. Sometimes you can't get rid of the chain structure. It's always there. So this will somehow have to be added in. Why? I mean, in case you wonder, there's people who just like new ways of looking at things, but in case you wonder if this is good for anything or where it might be applied, this would be for modeling very large protein assemblies. What I've shown here is a virus capsid. This is maybe one of the most frequently cited case. You can look at a ribosome, which is not just proteins, but there's lots of protein material in there. And for all these things, I would say the standard approach of moving from atomistic to coarse-grain models has its limits, because there's always the idea of a grain. So there's always the idea of a point or representative object. And from a certain length scale, this doesn't really make that much sense anymore. And I think that continuum models are more reasonable, at least worth a look. Okay, so I'll start with how to make the link between the atomic molecular scale and the macroscopic scale for proteins. My main tool for this is the elastic network model. This is actually a family of models which has been around for about 20 years. And I think most of you have probably at some point seen the term or seen papers using this. So it has become quite widely used. There are many varieties, so I don't want to discuss the zoo. I just tell you the one I'm using so that you know what I'm talking about. So the model I'm using is you take the positions of the carbon alpha atoms and put something there, some coarse-grain particle, whatever you want. And the interactions are described by springs, in principle between all pairs. We'll see later that with increasing distance, the force constant decreases to the point that I didn't even draw the very long ones, which would cross the thing completely. So this is again lysozyme. Everything I do is on lysozyme, so only lysozyme pictures. So yeah, the interactions are this. You have a simple potential, which is given as a sum of all pairs. So this is really as simple as it can get. But of course, we need to define what this pair interaction function actually is. Again, there must be hundreds of articles, well, at least around 100, that propose various functional forms and so on and so on, discuss the relative advantages, disadvantages. It's not really that important in my opinion. The best I've developed myself is from 2000. I haven't found anything better since then, so I'm still using it. So this is what it looks like. Again, this is from the previous slide. And so this is the pair potential is a spring hook potential. So all that really counts is to know the force constant, and this is a function of the equilibrium distance. So this is always harmonic models. So you have an equilibrium configuration, and you look at deviations from it around the minimum. So this is the minimum deviation. So this is only the distance in the minimum, and this is what I use for that. Now I actually see that I forgot to actually write the functional form for the drawn outline here. This is a 1 over r to the 6 dependence here. And it's valid for everything except for the shortest pairs. Now, of course, there's no, the crosses are experimental observations. So there's a reason why there are two groups here. This is the neighbors along the chain between two neighboring C alphas, and that's everybody else. The nice part is that there's a clear separation in distances, so I don't need to make explicitly a difference between neighbors and non-neighbors. I just have a distance dependent, and the neighbors happen to be along 4 angstrom, and everything else happens to be significantly bigger. So it makes life a bit easier. So such models have been used by lots of people for studying lots of aspects of proteins. Flexibility, most of all, I think this is the core idea to see what happens if you put external forces on your protein. How does it deform? What happens? And then you can, as a next level, discuss, for example, dynamical domains, which are analysis of flexibility in terms of clusters. You can look at conformational change. This has been done quite a bit. And a somewhat different approach is to use these models in the interpretation of low-resolution images, in particular from electron microscopy. So, summary of the literature is that these things work. So there are many things that you can usefully study with elastic network models, despite the fact that they are rather simple. I think here we have an audience mostly of physicists, so it probably is not a problem. But in the beginning, I had a very hard time talking to biologists. I use a model where side chains don't appear and all residues are equal. I say this can't possibly represent reality. This is the really important part of protein is side chains. But again, I'm looking at folded proteins. They are folded. So and once they are folded, they're actually pretty dense matter, basically. Okay, so this is a coarse-grained model, one step up from atomistic models, but it's a coarse-grained model, but still with points, and they correspond to atoms. So there's still a very clear link to the atomic structure as they are experimentally determined. So what then? From there to continuous media. Now the idea is that you can what my goal is to describe proteins as objects with made from some elastic material, something like rubber or whatever. And so what I need to get to is a description in terms of material parameters, density and elastic tensor particularly. And then I'll do that, and then of course the practical question is does this work at some useful length scale? So how small can I make my system and still have something that is reasonably described by this kind of approximation? And the object I'm using for establishing the link is protein crystals, because these are actually macroscopic objects. We have taken some pictures from Wikipedia. So they're typically a couple of millimeters long. So the length scale here is millimeters for good crystals, that for proteins that crystallize well. If you have difficult cases, you may only get microcrystals and have much smaller systems, and they are more difficult to use. But let's say there's plenty of proteins for which you can get millimeter-sized crystals. And then at the atomistic scale, this is what it looks like. And there again, I can use lysozyme. So here inside the box is the unit cell. So the crystal is a periodic replication of this blue box. And inside each unit cell, in the case of this lysozyme crystal, there are 8 copies of the molecule, and I've made them in different colors, and then around is the periodic replication. So the unit size, so you had a length scale of 77 angstrom, 37 angstrom, that's the size. Again, every protein has its own, but it's always on this tens of angstrom length scale. So what can we do with protein crystals? Well, people produce them for doing crystallography, for resolving the atomic structure. But there's other things you could do with that. And in particular, as I'll show, you can do other experiments on them. And unfortunately, people aren't doing that as much as I would like to. I haven't really found that many of them. So if any of you knows about other experimental sources on protein crystals or are willing to do them, please get in contact. As a side note, there's people who have been looking at using protein crystals as nanotechnology to build catalyzers and so on and so on and so on. I'm not really an expert on this, but just to tell you that protein crystals are not just for crystallography. So these are the experiments I found. There's a group in Japan. This is more or less the first and last paper I have. I didn't want to. So they've been spending quite some time on measuring the elastic constants of protein crystals by measuring the speed of sound along each particular direction in the protein. And what has varied in the course of time is their approach to actually stabilizing the crystal, because the problem is the protein crystals are nice, large. You have a millimeter-sized object, but they're extremely fragile, and doing experiments on them is not obvious. You can break them very easily. So they started out drying them with less water constant. So they shrink in size and become more stable. And then they added other molecules to stabilize them mechanically. But unfortunately, this is really the only precise experimental data I could find on protein crystals other than crystallography. I would love to have more. Okay, so the idea is that given that we can make a model, the elastic network model, which you can apply to one protein, but also to a whole crystal. Nothing changes. You just have more interactions to compute. And you have experiments on the macroscopic properties of protein crystals. So they can make the link between the two. You can make a link between the macroscopic length scale and the microscopic length scale. And what I've been doing is I've computed elastic constants for the two models, the continuum model and for the atomic or near atomic ENM, and compared them to see how well this works. The approach, the technical approach to do this is normal mode analysis. So I'm looking at vibrational motions of a crystal. This is the equations of motion. This is nothing else but Newton's law. And this is old, right? I'm not. This goes back to, I think you can find it in the book of Max Born. This is old stuff. I'm not claiming there's anything new in there. I'm just showing it. So you have the equations of motion. You start with the idea that the result is a plane wave, and then you put this in and you see what happens. So you get the normal mode equations here. Here I have a sum in principle over infinite replicas of your unit cell. And what happens in the end, you have to solve these equations. This is something you compute from your elastic network model. This is an amplitude. This is a Q, a wave vector. So for every wave vector, you can choose any value of a wave vector. And whatever value you choose, you will get 3 n normal modes, where n is the number of, in my case, the alpha atoms, the number of particles. And you get, as a result, 3 n frequencies, and for each frequency, a set of amplitude displacement vectors. What's also important to know is there's two categories of vibrational modes in crystals. Out of these 3 n normal modes, you have 3 so-called acoustic and 3 n minus 3 optical modes. The difference is in the acoustic mode, you have the whole unit cell that moves like this, or the whole large assemblies, whereas in optical modes, you have relative motion of of piece part inside the of different atoms inside it. So when you go to very, very small wave vectors, so long wavelength, then the frequencies of optical modes go to 0 and the acoustic modes go to 0 and the optical modes don't. Why is this important? Because if you move to a continuous medium, then what is left over is the acoustic modes. Okay, so unless you care about technicalities, you can take a small sleep. I just wanted, for those people who know such things, I don't want to leave the impression that I'm glossing over this, because there's doing this practical elements and work, but you don't need to understand this in detail. There's a practical problem because you can't compute an infinite number of wave vectors for an infinite crystal. You can't compute with infinite crystals if you have an atomistic model at some point underlying this. So what I'm really looking at is a two-level periodicity. So I take my unit cell, I make a small number of identical copies of it, and then I consider this assembly periodically replicated in space. So what I'm studying, I'm computing for, is more than one unit cell, but not an infinite crystal. It's something in between. And then I can look at limits. Crystal properties here for I can extrapolate to an infinite number of unit cell copies in my crystal I'm studying. Okay, as for relaxing, you can look at what these things look like, just to give you some idea. Although it is very hard to see anything in these pictures, in my opinion, so I don't really want to do an explanation of this. So now I'm moving to higher level modes. So you see the numbers has been increasing. So with higher, you go to faster motions and more localized motions and smaller amplitudes, as always with normal modes. Okay, this was the elastic network model applied to a crystal. Now let's do the elastic medium approach. I start with an overview of the description. So now I don't have atoms anymore, no particles, no grains, no nothing. So what my change, my deformation of my object, my material is described by a displacement field. So at every point in space there is a displacement vector. And then deformation means you have relative changes locally. So you have a strain tensor, which is the derivative, the combination of derivatives. So why did you need the combination of derivatives? Because there's also rotation. Local rotation is also a change, but it doesn't make it a linear information. So this is the non-rotational part. And then this is linked to the stress tensor, which describes forces. So this is actually Hooke's law, for written in terms of elasticity. Yeah? So for a simple spring, this would be force equals force constants time elongation. And this, in the more complex world of non-isotropic media, this is what this gets. And again, you can do normal modes, and you get a wave equation. This is exactly the same. You have for each wave vector 3 modes, which correspond to the acoustic modes, as I said before. And this thing is a 3x3 matrix, which depends on the wave vector and the elastic tensor. So this is something. It's not a complicated formula. Okay, so let's compare. This is really the goal of the whole procedure. Let's compare the two. So the straight lines are the elastic medium. This is typically called dispersion relations. Well, this is simply the frequency, the vibrational frequency, as a function of the wavelength or wave vector here. The wave vector is normalized by 2 pi, so this is inverse wavelength. So you can read of the length scales here. 001 is 100 angstrom, for example. And if you look at these things, then you see the drawn-out curves from the elastic network model. They show pretty linear behavior initially, and at some point they start doing different things, and this is where you see the local structure of your material. It's no longer a continuous homogeneous medium. But well, where does this happen? No? It's around here, I would say. Yeah? So when you're at 200 angstrom or beyond, you can safely use the elastic medium approach. Now, as I told you before, the unit cell for lysozyme containing 8 copies of the molecule is 77 angstrom, so you're roughly 3 times 3 copies of the unit cell in each direction. So it's not ridiculously large. I mean, you can do something with that. If you looked at something like a virus capsid, you have comparative length scales. So you can actually use an elastic medium description at length scales which are still interesting for biological objects. It's not an artificial. It's not just protein crystals. I mean, that's the message. Because you may not care about protein crystals, so that's okay. I'm fine with that. And then you can go on and actually compare the elastic constants. I won't go into any details here. It's there's a paper with all the details comparing to. This was not very intelligent. Comparing my calculations for various systems to the measured values here. The agreement is neither great nor catastrophic. It's kind of in between, and we can discuss why the differences come from, and it's interesting. But I'm not going to go into this today. There's a paper on that. So the message is it's on the level of the simple models, simple physicist models. This is pretty decent. Okay, so let's take a step back towards smaller length scales. What do you do if you care about the stuff that happens at less than 200 angstroms? Can we do better? And I'm not going to provide an answer because this is more or less ongoing work. I'll just show you what the ongoing work looks like. So what we would like to have is something like this. This is what biologists like to look at, and the visualization programs do these kind of cartoon representations where every helix becomes a cylinder and a sheet becomes a flat thing with an arrow on this, and everything else is just some strand. The problem with these things is they are made. These are graphical representations for the human eye. They correspond physically to nothing at all. And if you actually compare different programs making cartoons for the same protein, the helices are in a slightly different place. So that if you look at it from far away, it's okay. But there is no exploitable detail. There's no obvious relation. Why does the cylinder stop here and not there? There's lots of arbitrary decisions made by programmers, not for describing physical reality, but having something which gives a clear picture to the human eye. And I'm insisting a bit on this because this is a problem in many other areas. I've had this problem quite a bit in working with data from electron microscopy, which is also pre-processed for visual inspection. And you don't get the raw data, you get the processed thing, which was made to be clear to the eye, and it has lost any physical significance. It's very hard to work with such things. Okay, here this is different. This is a computational model. You just say, okay, it's an inspiration, but we don't actually use it. So what can we do in a more systematic way? I'll first outline this graphically. So first we define an axis going through the protein. So here we have this black line I've already shown earlier in the plot. This will come up again, which kind of simplifies sheets and helices by making them straight. So we get rid of one level of geometric detail. The peptide chain winding around the axis. So this is joint work with Gerhard Kneller, who's over there. You have seen him this morning, but he didn't talk about it. Sorry? I'll come to that. Yeah, that's the topic. And then after the axis, so this is the overview part. After the axis, we want to even go one step further. This is done. This is also done, but it's not really exploited yet fully. And actually define something like pieces of tubes, discs, some small cylinders. So making a protein model, which is basically stacked up small cylinders. And then we can assign physical properties to each cylinder and work with the total, but this hasn't been done yet. So yeah, how do you do that? So let's start with a curve. So this is for an alpha helix. This is really one of the alpha helices of lysozyme. This is not an idealized helix. So this is 3D projected. So you don't necessarily see that this is but this is of course the helix here winding around. So there's these alphas, and the lines between are just to guide the eye. They correspond to nothing. So what we do is we define triangles defined by 3 consecutive C-alphas. And then you look at 2 consecutive triangles. This triangle here, you have this triangle and this triangle. They actually geometrically almost similar triangles because the local configurations are very similar. So you can do a superposition, optimal superposition of one triangle to the next one. And that defines you a motion in space, and every such rigid body motion can be written as a screw motion. Screw motion meaning that you have an axis, you have this arrow, and the total motion is a translation of the along the arrow and a rotation around the arrow. So this can always be done. This is called Charles' theorem. This is very old mathematics. So that's what we do. So we end up with a screw motion, which is this arrow and this curved segment here. It's always a helix segment. And now we can do this along the chain. And then we can, so you get the helix as a mathematical curve in space. And you can also get rid of the arrows and just make a straight axis in the place. So this is our definition of the axis. So this is what's left. So we have the detailed curve of the peptide chain, which has been smoothed out to be a mathematical curve. And you could now remove the dots, the blue dots, and you still have a curve. And you have the smoothed out version, which is the axis here. I'll do this once again for a beta sheet, just to show that it can be done as well. That was a bit quick, maybe. Yeah. So here you have the two triangles and the motion between them, and then you extend this to the whole beta sheet, 2 strands, and you keep the axis. We actually don't do much with this helix strands around it. So this also to show that actually a beta sheet, it may be flat, but it's also kind of helix. And in fact, in a peptide chain, everything is something like helix. It's the geometry of the amino acid that makes that, for the fact that you always have winding around something, simply because of the geometry. And this is the part which we abstract away, which we throw out here. A beta sheet is just the helix where the consecutive atoms are on the plane, because the rotation is always 180 degrees, so it's nearly flat. But it's still a helix. So it's a convenient. I mean, you can, yeah. I think they can certainly find different definitions, which will be very, very similar. No, it's not an optimum, whatever. It's convenient. As I said, what remains to be done is to actually do the next step and develop this into a physical model with mechanical properties, and this is something we are working on. And then, yeah, of course, once it's done, see what this brings in terms of quality of a model. How much does this give us? It's an open question. This now a technical side remark, nothing to do with the subject today. It's just one slide. That this is an approach I've been adopting for a couple of years, and this was one of the recent studies that we did using this system. I was a bit fed up with seeing all this computational work where you don't really know what happens, because all the details are in some piece of computer code which you maybe never see, or maybe some version of it is public and you don't know where exactly, and you don't know which parameters were used, and it's always a bit when you really want to understand to the last detail what was happened, you can't. At some point you stop because you don't have the information. And there's a whole movement that was created around this problem, and which is 20 years old by now, but only gaining momentum more recently. And it was geophysicists from Stanford, John Claerbout, which gave it the title Reproducible Research, which is a bit of a provocative statement, saying that, well, everything in research ought to be reproducible, computations aren't. Okay. After this marketing speech, for this particular study, you can download a file which contains all the code and all the data and all the structures and input, output, and you can look at all the code, you can rerun it, you can reproduce the figures, you can run it again, you get the same PDF figures, and then you can say, okay, I want to see how they computed it. I want to change the parameters, see what happens. I want to change the definition of the axis, for example. Go ahead, do it, plug it in, and redo it for yourself. And you can, of course, reuse it as well for your own research. So, end of the publicity. The last part I want to discuss is an ongoing work to integrate, not just go beyond elasticity. Of course, you can always say I have a protein crystal and has elastic properties, but this is always an approximation. It is not a perfectly elastic material, and there are frictional relaxation processes in proteins which matter, especially if you want to look at something with a real time scale. For many applications in biology, you don't. People are perfectly happy looking at just flexibility, seeing how things deform, and they don't care if it's happening on a time scale of 1 or 10 milliseconds. And then you would probably don't need these things. But if you have real dynamics, like what you've seen this morning with neutron scattering, you have real time scales with picoseconds and so on. So you have to take into account frictional relaxation. Yeah, you have seen this morning. So if I had known that Gerald was doing this talk before mine, I would perhaps not even have put the slide, but it was not planned like this. Doesn't matter. Bit of repetition always does some good. So you have you can look at these motions in different length scales. And here I've just schematically drawn two ones, the famous potential energy landscape that everybody imagines according to the needs of a particular case. So I'm working with harmonic models, as you've seen all the time. So these are parabola, and you have one which is which gives kind of the global envelope of what is possible in terms of deformation, elasticity. But you also have fast vibrations happening more locally, and which, when you look at these things, basically disappear in the description, which based on diffusion. So what you look at on this scale is not vibrational motion, but hopping back, forth, and so on, and this ends up being diffusive motion. So yeah, slow diffusion. What is the appropriate physical description? The one we picked is Brownian dynamics. You could consider Langevin dynamics, but well, it's a long discussion. Brownian dynamics is pretty good for this, as we'll see. You get some effective potential which you need to get from something. Well, actually, there's something I didn't really say when I showed my elastic network model, that the interactions were actually derived from an all-atom model for fast vibrations. So it's actually the wrong one. My elastic network model, the potential is for the red curve, not for the green one. And the approach that I've adopted is simply to multiply this by a constant factor, and this works. I think many people have made this observation. It's easy to see why this is not completely absurd, but I'm not aware of a real justification for it. There's also the assumption that of independence between the motions in these two length scales and time scales. And then you have this diffusion equation for P, which is the distribution of position, the function of time. And then here you see again this force constant matrix for the harmonic potential, but you also see a friction matrix here, which needs to be defined. And the solution of this is well known. Again, this is very old physics. It's the Ornstein-Uhlenbeck process, which describes diffusion and harmonic potential. So again, this is here in the papers. It's actually Gerald Tiller who did the theoretical preparation for this, and then we did together with experimentalists a study applying this to proteins. You can still, and this is maybe less known, these equations are old and the Ornstein-Uhlenbeck process is old, but if you have an Ornstein-Uhlenbeck process in 3n variables for n equals a couple of hundred, it is actually convenient to use the normal mode approach again. And you can define something similar as for vibrations. You have your harmonic potential here. There are various ways to look at normal modes. The standard normal modes from the literature are those vibrational modes, which are the eigenvalues of the mass-weighted force constant matrix that gives you the vibrational frequencies as eigenvalues. You can actually not use the mass weighting and you get force constants. I think this is actually much more convenient for many cases than the second one. And what you're looking at now is this one. So you look at a friction-weighted force constant, and the eigenvalues are relaxation weights. So what are these modes? These are not independent motions in this case. For diffusion, it doesn't really make much sense. But you can look along each direction of a Brownian mode. You have a relaxation with a single relaxation time. And then when you look at all the mixture, you have a whole spectrum of relaxation times. So we still need to get the friction constants from somewhere. So as for the potential, this was done by reference to the comparison to all atom molecular dynamics simulations. This was a trajectory which we happen to have. Our experimental colleagues had done this for different purposes, and we just reused it. So this is why this is not lysozyme, because we do everything in lysozyme. But this is C-phycocyanin. I don't really know why this was chosen. Doesn't matter. Anyway, it's supposed to be a universal quantity, so it shouldn't matter which protein we use. And what we found, looking at the MD trajectories for this simulation, this was, for example, with a water shell, I should add. So I didn't show it, but there's a water shell around this. That you can actually say the friction constants are actually very nearly proportional to the density in the sphere around each point. So if you want to know the friction constant for this this point here, this area of the protein, you draw a sphere around. I think it's 2 nanometers size radius, diameter. You compute the density averaged over this. You read off the corresponding value here. What does this mean? This means that the more protein atoms are in your surroundings, the more friction there is. That means the friction comes from the fast interactions with other protein atoms. If you think this is evident, it's okay, you can stop here. The point is, I think there's an enormous amount of literature which claims the opposite, which claims that friction is a solvent effect. I think there's absolutely no basis for that. I've never even seen a basis for it. It's simply an assumption that is repeated, and they cite other people for having said it before. It's wrong. Constant for, yeah. Yes. Yes.
So you also have an assumption. So I don't know if your assumption is correct, but you also have an assumption here that the friction for every bead is the same, right?
No, it's not for every bead. It's not the same. It's for no. I said for every bead, I read off from this graph what the friction constant is. I assume that this graph is universal, but not anymore. So I take for every C alpha in my model, I compute the surrounding density of atoms from an all-atom model, and then I read off the friction constant. It's not constant, no. And I said it's checked in a sense. I mean, you can believe or not molecular dynamics simulations as reference, but there's something. It's not invented. There's a basis for it, which may or may not. I mean, the simulation was maybe not the best, and I don't know what the force field impact is, and so on and so on. There's many things that could go wrong, but there is a basis from it. No, it was a simulation of a protein in a water drop. So there's a shell of water molecules, but it's finite, with a restraining potential to keep the water from evaporating. The simulation were done originally for comparing with neutron scattering data, and the idea was to have the correct ratio of protein to solvent to represent the powders are used in neutron scattering. And since nobody knows what these powders are, I said, okay, let's just do this. So it's a protein in a water drop. Just to show that since this was done in the context of neutron scattering, in collaboration with neutron scattering people, the tests we did were based on neutron scattering as well, although there's unfortunately no experimental data. At the time, there was the hope that with spin echo techniques, one could measure these things, and for some reason it never happened. The instrument wasn't ready, and then people left. It was never done. So all this is simulation data. The red curve is molecular dynamics data simulation, the same simulation used for the friction constants. And the blue curves are our Brownian modes. It's not so bad for a simplified model, going from all atoms with charm, whatever force field, and water, and so on, to a description with 129 beads, some springs, and some force constants. So doesn't look so bad. Except that, well, of course, you can always do better. Then again, this is something you have seen this morning already. This is the exact same work, the same formulas you have already seen. It's again joint work with Kneller about anomalous diffusion in proteins. So this is here. This is Brownian modes plus vibrational terms. That we had this idea of independence between some short-term vibration and some long-term diffusion. But now we are thinking that perhaps this is not the right picture, and the right picture is to use a single anomalous diffusion model for the whole thing, and that remains to be applied to normal modes. It's something I would say this should be straightforward. We should do this. Yeah, we should do this. So this study is for individual C alpha atoms, analysis of the MD trajectory. So this is not Brownian modes, not harmonic force fields, nothing. It's actually an analysis of molecular dynamics relations. But then the next logical step would be to combine this with the previous one and get something like anomalous diffusion normal modes. Again, remains to be done. Oh yeah, this is the so this remains to be done, as I said. And then the next thing that remains to be done would be to link this to macroscopic viscoelastic properties, and that the idea would be that the visco is diffusive stuff and the elastic is elastic constants. I don't really have a much clearer idea of that than this. So this is, in particular, it would be nice to be able to measure viscoelastic properties of for example, protein crystals. But as far as I know, nobody has done this. So that's again the problem of the experimental reference to create something credible. So this is a more complicated. So I think the first thing is probably just an exercise. We'll see when we've done it, but this part is more complicated. Okay, so that means I'm almost done. So the idea is to go to a coarse, larger scale description, but not grains. So as you've seen, the idea is to get to instead of going from many points to fewer points, to go to a description of homogeneous materials, less homogeneous materials, but always without any smallest length scale and without any grains or reference point, arbitrarily chosen reference points. So this is kind of summary. The continuous minimum approximation starts to be useful for length scales around 30 nanometers. Within a safety margin, which is quite decent already. And then we could probably go to intermediate descriptions somewhere between this and the atomic scale without introducing grains. Friction effects are definitely important when you look at dynamical models and timescales, and they need to be put in. And then one maybe not so obvious comment is that this is kind of a physicist's dream because you can do nothing but harmonic oscillators, harmonic models all the time. And why is this nice? Other than that we've all done this at some point and we like it and we understand it. At this point, we understand this. So most atomistic simulations are done using models with thousands of parameters and thousands of atoms, and these parameters have been compiled using various methods that are not really described coherently anywhere. You don't really know what the limits of these things are, and when something goes wrong, you can just say, okay, this model is not, this force field is not good for this quantity, but you don't know why. So you have described a complex system with a complex model, and you don't understand your model any better than your original system, but you control it. Here, actually, you have harmonic models, and you can actually, if something has weird behavior, you can very probably figure out where it comes from. So in terms for understanding what's happening, harmonic models are nice. It's not just ease of computation, it's also ease of understanding. The last remark is that we always have to think about systems for experimental validation of everything. As that the protein crystals are nice, they are easily available. 3D crystal, standard protein crystals for crystallography, but also 2D crystals. They are flat 2D crystals, and there are helicoidal crystals. It's a bit like a DNA assembly of strings of proteins. Both types are heavily used in electron microscopy. People know how to make them, and you can probably get some leftovers from your biochemistry colleagues if you ask them nicely. What is missing? And then there's natural protein assemblies, large scale, such as fibers and capsids. I think what is missing for all of this is experimental data. So I was hoping to have more experimentalists in the audience and saying, please do something for me, but it seems that most people here are theoreticians, so that's life. And that's it.